So I started recently rewatching this old series called Cheers, which takes place in a bar, and there's this regular who comes in every single day, probably an alcoholic. I mean, when it comes right down to it. And his name was Norman, and every day he would go, "Hey, good evening, everybody," as soon as he walks in, and they would all scream, "Norm!" Right, so that Norm and this Norm, not exactly the same thing, but that's what I think of every time I see this. Okay, so what is the norm? We're going to use this to help us define what a definite integral is all about. So we said that whenever we're talking about a Riemann sum, you have a function value times a width, and the width of that subinterval does not have to be exactly the same for each rectangle. If it is, it's a regular partition. If it's not, doesn't it make sense that one of them has to be the biggest? Okay, we're going to call that biggest one. The widest one, we're going to call it the norm. And the way that we write it is one of two ways. You can write it with a delta sign in here. So the delta is usually used as a partition, a symbol for the partition when we break it up into intervals, subintervals. And then we're going to put these double brackets here. It looks like absolute value, but we really wanted to make it positive. Wait, I wasn't sure the first one took. All right, let's put an extra set. That's what it looks like, right? Or we can just call it the max delta x sub I. So that notation probably makes sense. We're saying it's the maximum width. Delta x sub I is the width, a variable width, and we want the maximum. All right, so follow me here. The number of subintervals n that we have here and the norm are related by our partition formula. It's sort of like this, or not our partition, our regular partition formula, b minus a over n, right? So if they're all the same, doesn't this make sense? That the norm, which is the widest one, if they're not all the same, it has to be greater than or equal to that regular partition. Okay, does that make sense? Okay, so now what I'm going to do, since these are positive numbers, you can treat this in the same way algebraically as an equation, and we can switch out this n and the norm right here, and then take the limit. Let's see what the heck happens here. So we're going to take the limit as the norm approaches 0. What does that mean? We're talking about the width of the biggest rectangle in our subintervals. As we make that closer and closer to 0, we want to see what happens. So this b minus a over this delta x, that has to be less than n, right? If we switch these things around, that has to be less than n. So this is another way to interpret n, or at least something that's smaller than n. And does this also make sense? B minus a here is going to be a positive number that we're going to divide by something that's getting closer and closer to 0. Some number over 0 is going to approach infinity. What does that mean? It means that as the width of the largest subinterval approaches 0, well, we're going to get more and more rectangles to fit underneath the curve. They're going to start approaching infinity. So those two expressions are considered equivalent as the norm approaches 0 or as the number of rectangles approaches infinity. I point this out because the definite integral is defined in terms of either one of them, depending on which book you look in. So let's take a look then at the formal definition of a definite integral. If f is defined on a closed interval from a to b, stop. It doesn't say continuous, it just says defined. Okay, that's interesting. If f is defined on a closed interval, and also notice it doesn't say non-negative, because we saw from a previous example that it doesn't necessarily need to be. All right, if f is defined on a closed interval from a to b, and the limit as the norm approaches 0 of this Riemann sum here exists, we're going to call that function, this new word, integrable. Integrable just means that you can take the integral of it, just like differentiable means that you can take the derivative of a function. It's integrable on the closed interval from a to b, and the limit is denoted by, here's the new notation. So here's our limit of our Riemann sum, and it is equal to, the way that I read this is the definite integral from a to b of f of x, and this dx that's right here, it's like the differential. We usually read it with respect to x. Definite integral from a to b of f of x with respect to x. So the great thing about the notation is that you can see what our interval is. It's going from a to b. You don't get that information from this limit of the Riemann sum. And I guess a piece of information that's kind of missing here is the width. And you can see that as we take the limit as the norm approaches 0, the width here is going to get closer and closer to this differential here, this dx business. Okay, so this limit is called the definite integral of f from a to b. This a that's down here is the lower bound of our integration, and the b up here is our upper bound of our integration, the upper limit. Now, like I said, there is another way to write this norm thing, this thing that looks like a double absolute value of the delta symbol, and it could look like this. So it's the exact same slide in blue, now with this max delta x sub I. Oh yeah, but as the maximum width approaches 0, that is the same thing as the number of rectangles approaching infinity. And so usually, like for the sake of us writing problems down and stuff, this is the way that we evaluate definite integrals. Instead, we take the limit as n approaches infinity of this Riemann sum and call it a definite integral. And so we have been doing definite integrals since the last lesson. We just now have a nice, neat, new notation to summarize all this. We don't have to write all this stuff down. We can just write that integral symbol. As a matter of fact, on the AP Calculus exam, you would never be asked to evaluate the limit of a Riemann sum by hand. Instead, if you're given a limit of a Riemann sum, you recognize it as a definite integral, and then in the course of the rest of this unit, we're going to learn a whole bunch of ways to shorten this process because, my gosh, one problem takes the length of the entire AP exam? No, that can't happen, especially when they're going to throw quite a few of these at you. Okay, and so we're going to see that process shortening as we move through the rest of this unit.